For decades, computers have followed an astonishing trajectory. They've become smaller, faster, cheaper, and more powerful at a pace that feels almost magical. Smartphones now outperform supercomputers from a few decades ago. Artificial intelligence models run on consumer hardware. Moore's law, while slowing, reshaped the world. But batteries tell a very different story. Despite constant headlines about breakthroughs, batteries today feel frustratingly familiar. Phones still need daily charging. Electric cars still worry drivers about range. Laptops still die at the worst possible moment. So why hasn't battery technology kept up with computers? The answer begins with a fundamental difference between information and energy. Computers manipulate information. Batteries store energy. And those two things obey very different laws of nature. The exponential progress of computing was driven by miniaturization. Engineers learned how to pack more transistors into smaller spaces. Each transistor switch requires only a tiny amount of energy. As components shrink, efficiency improves. Information becomes cheaper to move and process. Batteries don't work that way. A battery stores energy through chemical reactions. That energy comes from breaking and forming chemical bonds. Unlike transistors, chemical bonds cannot be miniaturized indefinitely. They are governed by atomic physics, not engineering ingenuity alone. This creates a hard ceiling. Energy density, which is how much energy a battery can store per unit of weight or volume, improves only slowly. Lithium-ion batteries, which power most modern devices, are already close to their theoretical limits. Over the last 30 years, battery energy density has improved by only a few percent per year. Nothing like the exponential gains seen in computing. Another key difference is safety. A battery is not just storage, it is a controlled chemical system. Push it too far, and it becomes unstable. Overcharge it, puncture it, or overheat it, and the results can be catastrophic. This means battery engineers are constantly trading performance for safety. Higher energy density increases the risk of fires, explosions, and degradation. Every gain must be carefully balanced against reliability and lifespan. Computers can crash and reboot. Batteries can burn. This alone slows progress. Manufacturing also plays a major role. Computer chips benefit from extremely precise, repeatable fabrication processes. Once a chip design works, it can be replicated millions of times with minimal variation. Batteries are far messier. They involve materials that degrade, expand, contract, and age. Small imperfections during manufacturing can significantly affect performance and safety. Scaling new battery chemistries from lab experiments to mass production often takes decades, not years. Many promising battery breakthroughs fail not because they don't work, but because they don't scale. Cost is another constraint. Batteries require large amounts of raw materials like lithium, nickel, cobalt, and graphite. These materials are mined, processed, and transported globally. Supply chains are fragile, expensive, and often environmentally damaging. Improving batteries is not just a scientific challenge, it is an industrial one. Electric vehicles make this problem more visible. People expect EV batteries to improve as rapidly as computer chips, but the physics simply doesn't allow it. Doubling range means roughly doubling stored energy, which means more weight, more cost, and more safety challenges. This is why much of the progress in electric vehicles comes not from better batteries alone, but from better software, lighter materials, improved aerodynamics, and smarter power management. Software can improve efficiency far faster than chemistry can improve energy density. There's also a psychological factor. Battery improvements feel disappointing because expectations were shaped by the computer revolution. We subconsciously expect all technology to advance exponentially, but not all technologies can. Some domains, like computing, benefit from abstraction. Others, like energy storage, are tied tightly to physical reality. Atoms do not scale the way bits do. That doesn't mean battery research is stagnant. It means progress is incremental. Solid-state batteries, lithium metal anodes, sodium-ion batteries, and alternative chemistries all show promise. But each comes with trade-offs in cost, safety, durability, or scalability. None represent a sudden leap comparable to the transistor revolution. The future of batteries will likely be evolutionary, not revolutionary. And this leads to an important conclusion. The reason batteries haven't improved as fast as computers isn't a lack of innovation or effort. It's because energy is harder than information. Storing and releasing energy safely, cheaply, and reliably is one of the most difficult problems in engineering. Computers became powerful by shrinking switches. Batteries cannot escape chemistry. Understanding this helps set realistic expectations. It explains why charging anxiety persists, why headlines repeat themselves, and why true battery breakthroughs are rare. Progress will continue, but it will be slow, careful, and constrained by physics. Sometimes technology doesn't move at the speed of ambition. It moves at the speed of atoms. If you found this explanation useful, like the video, subscribe to Talking Tech, and share it with someone who's still waiting for a battery miracle.